A simultaneous equation occurs when we have multiple different relationships that we need to all be true at the same time. First, consider the relationship y minus 2x equals 6. This means that the variables x and y must be such that they make this equation true. For example, y could be 16 and x 5, or y could be 4 and x minus 1. If we make y and x the axes on a graph, we can draw this relationship. Rearranging to our usual y equals mx plus c can tell us the relationship is a straight line graph with a gradient 2 and a y-intercept of 6. Every point on this line has x and y coordinates, which makes this relationship true. Look, here is 5, 16, and here is minus 1, 4. Now we introduce another relationship. Let's say we need 2y plus 4x equals 20 to also be true. There is another list of pairs of x and y values which makes this equation true, and we can again draw these points on the graph. We rearrange to see this is a straight line graph of gradient minus 2 and y-intercept of 10. Every point on this line has coordinates that satisfy the relationship 2y plus 4x equals 20. Now, if we required not just one of these relationships to be true, but both of them to be true, what does this correspond on the graph? Well, if we want both these relationships to be true, we need the x and y values to be such that they lie on both of these lines. This means we are after the coordinates of this point at the intersection of the two lines described by the required equations. To find the coordinates of this point, we use a technique called substitution. We take our first relationship, which says that y minus 2x must equal 6, or equivalently, that y must equal 2x plus 6. Our other relationship says that 2y plus 4x must equal 20. To merge these two, we impose the first relationship onto the second. We say that since this tells us that y must equal 2x plus 6, we can just replace any y's we see in the other equation with 2x plus 6. We have substituted 2x plus 6 in for y. We could have equivalently rearranged to say x equals y minus 6 all over 2, and then replaced all the x's in the equation with y minus 6 over 2. Now this equation holds the information of both of the relationships and is just in terms of x. We can easily solve this to see that x must equal 1. Once we have obtained x, we can refer back to either of the original relationships to see what y must be. If we have done this correctly, it does not matter which equation we use. We quickly see that y must equal 8 to satisfy either equation. Thus, we have found that the values that satisfy both equations simultaneously are x equals 1 and y equals 8, and these will be the coordinates of the point of intersection on the graph. This approach also works for simultaneous equations involving more complicated relationships, such as quadratics. The only difference is you have a harder equation to solve.